Mechanical Power Transmission, Part 1 of 2. Unit Objectives. The students will be able to demonstrate how mechanical power transmission systems are very important in the design and construction of competition robots. The students will be able to vary the gear ratio and the mechanical advantage in a system that gives them the versatility necessary to accomplish whatever work needs to be done. The students will be able to determine gear inputs and outputs by calculating the difference between them and determine their gear ratio accordingly. Introduction. DC motors have a limited amount of power that they can output, which means that for a specific amount of work, the motor can only do it so fast. This unit will show how gear ratios can be used to adjust advantages so that the motors can do the work more slowly within their power limit. Simple machines. There are 6 types of simple machines: lever, pulley, wheel and axle, inclined plane, wedge, and screw. The lever, pulley, and wheel and axle make up the lever family. The inclined plane, wedge, and screw make up the inclined plane family. Input, output, and mechanical advantage. All simple machines have an input value, whether it is distance like a ramp or force like a wedge. All simple machines have an output distance or force. Mechanical advantage is the ratio between the output force and the input force. It is also the ratio between the input distance and the output distance. Compound machines. A compound machine is a machine that combines 2 or more simple machines. Power transmission. Power is the rate at which work is performed. Power transmission is defined as the transfer of energy from its place of generation or storage to the location where it does work. Example: electrical energy is stored in a battery. It is then transmitted through wires to a motor where it is converted into mechanical energy to do work. Gears. VEX uses a 4-sided square polygon shaft as part of its motion system. This means that the shaft will transfer torque directly to anything with a matching square hole. Spur gears. The most common type of gear is called a spur gear. Spur gears transfer motion between 2 shafts running parallel to each other. Spur gears are characterized by their teeth, which are straight and parallel to the gear's axis of rotation. Bevel gears. Bevel gears are conically shaped and transmit power between shafts that have intersecting axes of motion. Bevel gears can transmit power between shafts at a variety of angles, but are most commonly used to transmit power 90 degrees. Crown gears. Crown gears are a type of bevel gear in which the teeth project perpendicular to the gear face. Worm gears. Worm gears come in pairs, worm gears and worm wheels that mate together to transfer power between perpendicular shafts to have axes of rotation offset from each other. Worm gears resemble screws. As they spin, they turn their mating worm wheel. In this type of gear pair, the worm gear can drive the worm wheel forward, but it is very difficult for the worm wheel to drive the worm gear. The gears are useful for applications where a designer doesn't want a mechanism to be back-driven. Helical gears. Helical gears resemble spur gears, only their teeth are curved in the shape of a helix. These gears can be used to transmit power between 2 parallel axes of motion or between perpendicular non-intersecting axes of motion. Epicyclical or planetary gears. An epicyclic or planetary gear set consists of 1 or more planet gears moving along an outer ring gear as a central sun gear drives them. One might use the sun gear as the input and the planet carrier as the output while the ring gear is held stationary, or one might use the ring as the input and the sun gear as the output while the planet carrier is held stationary. The overall mechanical advantage of a planetary gear set changes depending on the configuration used. Rack gears. A rack gear is a gear mounted on a straight rod such that it moves in a linear fashion when torque is applied to it by a spur gear, also known as a pinion gear. Rack and pinion gear sets are commonly used to convert rotational motion into linear motion. Cars utilize this type of gear set to convert the rotary motion of a steering wheel into linear left-right motion required to steer a car. Gear teeth and pitch. In order for 2 gears to mesh, they need to have the same size and shaped teeth. In your notebook, answer the following question. What will mesh with this gear? Is it 1, 2, or 3? More teeth equals a bigger diameter. Gear ratios. Gears are not just used to transfer power. They also provide an opportunity to adjust the mechanical advantage of a mechanism. One can see that if the input side of the lever moves 1 meter, then the output moves 4 meters. The difference is proportional to the ratio between the lengths of the levers. The interesting thing about this is that it moves these distances at the same time. Let's say it takes 1 second to move the input 1 meter, and the input is moving at 1 meter per second. At the same time, the output moves 4 meters in 1 second, and is moving at a speed of 8 meters per second. The output is moving faster than the input. Gear ratios. The same system now has a 4 Newton force applied to the input. How much force then results at the output? Torque equals the force times distance from the center of rotation, so in this case 4 newtons times the 2 meters equals 8 Newton meters. Force equals torque divided by distance, so our torque that we got from the 8 Newton meters here divided by the distance of 8 meters equals 1 Newton. The output moves 4 meters with 1 Newton of force. Gear ratios. One can see how mechanical advantage for levers can be used to harness a fixed input force to accomplish a desired output. Gears work in the same manner. A spur gear is basically a series of levers. The larger the diameter, the longer the levers. Torque applied to the first gear results in a linear force at the tip of the gear teeth. That same force is applied onto the tip of the tooth of the gear it is mated with, which in turn results in a torque rotating this gear. The diameters of the gears become the lengths of the levers, and the resulting change of torque is equivalent to the ratio of the diameters. Gear ratios. If the input 36-tooth gear is rotated 1 tooth, then the gear is rotating 1/36th of a revolution. As it advances, it moves the 60-tooth gear 1 tooth also. Gear ratios. As the small gear turns a certain amount in a given time, the larger gear turns a smaller amount. This means the larger gear is spinning slower than the smaller gear. Small gears driving big gears results in a speed decrease. Large gears driving smaller gears results in a speed increase. One can see that the ratio between sizes of two gears meshing is proportional to the resulting torque change and speed change between them. This is known as gear reduction. We can use teeth to calculate gear reduction. The gear ratio is denoted as the driving gear teeth, then the driven gear teeth. The gear reduction for the previous gears are 36 to 60. The gear reduction is calculated as driven gear teeth divided by driving gear teeth. The stall torque of the second shaft can be calculated using the formula output torque equals input torque times gear reduction. The free speed torque of the second shaft can be calculated using the formula output speed equals input speed divided by gear rotation. That ends part 1.